Welcome everyone to TCS Plus. Today we have Steve Fenner from University of South Carolina. Um, so before we start the talk, there's the usual announcements. During the talk, you will be muted. So if you have a question, you should unmute yourself and ask a question. We encourage questions. And so helping us with TCS Plus, Derived Graph, Thomas Hollenstein, Thomas Vidic, Gautam Kamath, and Keylemma Kanon. And now we'll go around the table and introduce all the groups. So we have the group from Waterloo. Hi, Waterloo. We have the group from Columbia. Hey, Columbia. Hey, Clement. We have the group from Michigan State. Hey. We have the group from Item Plus. Hey. We have the group from Caltech.
Good morning.
We have the group from Michigan Ann Arbor, and we are still waiting for a couple of groups to join. So, today so they will join in due course of time. So today we have Stephen Fenner. Steve is at University of South Carolina. Steve has produced a number of great results in classical complexity and quantum computation. And today he's going to talk about a problem which was open for a very long time about getting perfect matching to be in NC. It was known to be in randomized NC for a very long time, and he's going to talk about a result which finally gets a deterministic NC algorithm. So another randomized algorithm finally falls into the deterministic grid. So Stephen, welcome.
Thank you. Thank you very much for that introduction. Just a quick note. I can hear people, but I can't see them. I don't have the screen. So if you have a question, please identify yourself. And let me start by thanking the TCS seminar people for inviting me to talk. And I think this is a real special honor for me to do. And so let's get started. So this is a talk about bipartite perfect matching. We have a Quasi-NC algorithm for it. This is a fast parallel algorithm with a quasi-polynomial number of processors. And this is joint work with Rohit Gurjar and Thomas Tiroff. They are both currently at the University of Aalen in Germany. And here is a picture. Here's a picture of them, and I will leave it to you to figure out which one is which. This picture was taken at Kanpur, and just recently, a couple, I guess, a month or two ago. All right. So I'll introduce matching. I'm assuming most people know what this problem is, but I'll just do a quick intro. So we have a graph with n nodes and m edges, and a matching in the graph is just some set of edges such that every vertex is incident to at most one edge in the matching. And for perfect matching, every vertex is incident to exactly one edge in the matching. So that would be where every vertex is matched by an edge with some other vertex, a unique other vertex. And the perfect matching decision problem, PM, asks whether a given graph has a perfect matching. The search problem is similarly, you want to output a perfect matching if it exists. Otherwise, some default token say no. And of course, matchings and perfect matchings have been widely studied for a long time, both in combinatorics and complexity theory. And they have a wide range of applications, which I won't go into here. Okay. But we have some previous algorithms for perfect matching and the search and its search version. So a long time ago, back in the 60s, there was a polynomial time algorithm. This is known to be easy sequentially due to Edmonds, a polynomial time algorithm for perfect matching. And for the parallel case, there's Lovaas in the late 70s came up with a fast randomized parallel algorithm. So a feasible number of processors and using random bits, and determines if a perfect matching exists with high probability. This was also improved by Chari Rogati and Srinivasan in the 90s. There's a randomized NC algorithm for search PM. I'll define NC in just a second. This is due to Karp, Upfall, and Vigderson back in the 80s. And there's another NC algorithm due to Momoli, Vazirani, and Vazirani, also in the 80s, using the so-called isolation lemma. And I will come back to this because we are going to use this isolation lemma, or at least de-randomize it to remove the randomness. All right. So NC, this is the obligatory definition. NC is the class of problems with uniform polynomial size circuits with polylogarithmic depth. So depth log of n to some constant exponent. For these circuits solving perfect matching, for polylog depth circuits solving perfect matching, nothing better than exponential size was known, and then that's sort of the trivial upper bound is exponential size circuits. So the problem is still open. Is there a fast parallel non-randomized algorithm for perfect matching? In other words, is perfect matching in NC? This is still open. This is sort of the goal of all this work. We've come closer to it, I will say, than before. But there's also been work on the deterministic parallel algorithms. So there are NC algorithms for certain types of graphs. For example, graphs that don't have a complete bipartite subgraph, a K33. There's an NC algorithm to determine perfect matchings in these graphs due to Vazirani. Graphs having a small number of perfect matchings. This is also has an NC algorithm due to Grigoriev and Karpinski, and also improved by Agrawal, Huang, and Tirov in just less than a decade ago. There's NC algorithms that work on bipartite deregular graphs, Lev, Pippinger, and Valiant, and also Sharon and Vigderson in '96. They gave some improvements to this. Strongly chordal graphs, Dahlhaus and Karpinski, and planar bipartite graphs, Datta, Kulkarni, and Roy, and Tawari and Vinochandran, pretty recently, actually. So our work is in the bipartite case, and what we show is that the decision problem and the search problem are both in Quasi-NC. So what that means is that they're on bipartite graphs. We have uniform circuits of depth. In fact, it's log squared of n, and the size is 2 to the big O of log squared of n. So all we have to do is decrease the exponent by 1, and we've got an NC algorithm. We also give a randomized NC2 algorithm. The 2 means the depth is log squared for bipartite perfect matching using only big O of log squared n random bits. And previously it was only the best upper bound was a linear number of random bits. So I'm going to sketch out the RNC algorithm of Momoli and Vazirani using the isolation lemma, just to give you an idea of what's going on, and because our work is very much closely related to this. So if I have a graph that's move my own picture out of the way here. So yeah, graph G is bipartite, and it has a bipartition into left vertices and right vertices. And suppose we have a weight function. So this is a weight on the edges, positive integer edge weights. And if we have a weight function, we naturally extend the weight function to sets of edges where the weight of a set of edges is just the sum of the weights of the edges in the set. Okay, at this point what we do is we define the n over 2 by n over 2 square matrix, call it A sub w. And the entries of this matrix are if there's an edge from the ith vertex on the left to the jth vertex on the right, then the entry is 2 to the weight of that edge, and otherwise it's 0. Now, if you take this matrix and you look at its determinant, it turns out, and you take the determinant and you take sort of the completely expanded version of the determinant, where it's the sum of these exponentially many terms, so n factorial many terms, you see that every non-zero term in the determinant corresponds to a perfect matching. So the factors in a non-zero term match exactly one vertex on the left with one vertex on the right. And when you multiply the factors, you're adding the exponents. And so a non-zero term of the determinant looks like you take some perfect matching of G, and it's 2 to the weight of that, total weight of that perfect matching. But then, of course, you multiply by either plus or minus 1, depending on the sign of the corresponding permutation that you get. Okay, so what that means is that if G has no perfect matching, then this determinant is always 0 for any weight function W, because none of these terms are going to be non-zero. On the other hand, if G does have a perfect matching, then the determinant actually may still be 0, and the problem is because some of these terms are non-zero, but they cancel. So you could have a positive term canceling with a negative term, and it's possible that this determinant is still 0. So this doesn't give you a decision procedure for that. But in a special case, it does. So we'll say a weight function W is isolating if G has a unique minimum weight perfect matching with respect to this weight function. So if we can isolate a unique minimum weight perfect matching, and we have an isolating weight function that isolates the perfect matching as the unique minimum weight, then the determinant is guaranteed to be non-zero, because this matching, this minimum weight matching term in the determinant doesn't cancel with any other terms, because the other terms are strictly higher powers of 2. So the determinant will be non-zero in this case. So the isolation lemma of Momoli, Vazirani, and Vazirani is we let W sub E, we choose a weight function uniformly at random. So every edge we give a weight uniformly in the set 1 to 2m. Remember, m is the number of edges. And we do this independently for each edge. Then the isolation lemma says that this weight function is isolating with probability at least 1/2, assuming G does have a perfect matching, of course. So if W is isolating, then computing its determinant gives the correct answer. So we know that if we have an isolating weight function, all we have to do is compute the determinant, and this can be done in NC squared, an old algorithm from Berkowitz back from the 80s can do this. So computing determinants is in NC. So that's essentially the RNC algorithm of Momoli and Vazirani using the isolation lemma. So we want to de-randomize this lemma. That's our whole goal. And we can do so, but when we do so, we'll have weights that are not quite polynomial size. They're going to be quasi-polynomial size when we do this. So let's start with an isolating weight function. It's clearly isolating, but it doesn't work at all because it's not efficient enough, but it's a good place to start. So let's just number the edges from E0 to EM-1, and we'll just define the weight of the ith edge to be 2 to the power of I. Well, W is clearly isolating. Every set of edges is going to have its own unique sum of powers of 2, so no two sets of edges are going to have the same weight, so W is clearly isolating. But the problem is, of course, is that we can't compute the determinant efficiently because the matrix entries are just way too big. They're exponential size. So what we do instead is we reduce the weights modulo small numbers j. So this is a fairly standard trick that is used in other places.
I have a question.
Yeah, question.
Is it clear that there does exist a set of isolating weights? Like just the existential question.
Does there exist a set of isolating weights?
Like if I just choose weights randomly, does it? Is there a single sequence of weights which is isolating for any graph?
Is there a single sequence that's isolating for?
Or let's say
graph?
polynomial size set of sequences. Like a standard, like probabilistic, like a standard de-randomization.
Right. So you pick a polynomial sized sequence of weights, and does that work for all graphs? That I couldn't say. I couldn't say. Offhand, that's a good question. I'm not sure. So, but we know that a random for a fixed graph, a random weight will be isolating with probability at least a half. So what you can say, if you might be able to amplify that and find a weight function that is isolating for several graphs at once. I can certainly imagine that. But
so maybe just like if it's true that there exists, like if I just choose a random weight sequence with probability half, it's isolating for any graph, then just by amplification there exists a polynomial sized sequence of weights, like polynomial sized collection of sequence of weights, which such that at least one of them is isolating for every graph.
Yes, I could imagine that. So offhand, just thinking off the top of my head, I'm not sure how you would amplify it. But there's probably standard tricks to do that. So yeah, that's a good question. All right. Okay. All right. So we're going to reduce the weights modulo of small numbers j. So what we're going to do is we're going to fix an integer j, at least 1. So for any such j, we'll just define the weight function w mod j. Here, w is the weight function above. It just assigns the 2 to the I, to the ith edge. A w mod j is just we reduce that modulo j. So w mod j of the ith edge is just 2 to the I mod j, and we do that for all edges in the graph. So for some upper bound t we're going to choose later, let's take the set of all of these weight functions together. So for j running from 2 up through t, we'll call that capital W sub t. That's a set of weight functions. And this will be our set, and we will essentially choose weight functions from this set to apply to the graph. So this is the weight functions we're going to be using ultimately. All right, so to understand more about how to de-randomize the lemma, we need some background information. So I need to mention circulation. The concept of circulation, if I have a cycle in a graph, and suppose the edges of the cycle are given in cyclic order, so around the cycle, and assuming G is bipartite, P will be even, of course, even length cycle. So we have the following definition. Given any weight function, the circulation of C with respect to this weight function is, well, you just sum up the weights around the cycle, but you alternately add and subtract them. So you add one edge, and then the next edge you subtract, and then the next edge you add, and so forth. And you do this all the way around the cycle. And so this alternating sum is called the circulation of the cycle, and we will take its absolute value. So it doesn't matter where you start on the cycle, you'll get the same value because we're just taking the absolute value. And that we'll call that the circulation of the cycle with respect to the weight function W. So now, suppose I'm given a weight function, and I have two different matchings that are both minimum weight perfect matchings of G. So I have two distinct minimum weight perfect matchings of G. In other words, W is not isolating in this case. Well, M1 and M2 are going to differ on disjoint cycles. And each of these cycles is going to have zero circulation. So for example, I have maybe M1 is the blue matching, and M2 is the red matching, and here are the edges in the symmetric difference of the two matchings, so the edges that are in one and not the other. The claim is all of these cycles have to have zero circulation. And the reason is, well, suppose one of them doesn't, say the middle cycle. Well, if the middle cycle has zero circulation, then the blue edges are going to outweigh the red edges, or vice versa. The red edges are going to outweigh the blue edges. Anyway, the two sums of the two different colors are going to be different. Well, suppose the blue ones outweigh the red ones, for example. Then all we have to do is swap out the blue edges for the red edges in the matching M1, which is the blue matching, and all of a sudden we get a matching of lower weight because we've just replaced the blue edges in this cycle with red edges in M1. Their sum is less than the blue edges, so now we have a matching of lower weight, but that's impossible because we started with minimum weight perfect matchings. So we can't have non-zero circulation. All of these cycles have to have zero circulation if M1 and M2 are minimum weight perfect matchings. All right. We call these cycles nice cycles. Nice cycles are the cycles that you get by taking the symmetric difference of two perfect matchings. So one thing we'd like to do is we would like to choose a weight function from our set W sub t that gives non-zero circulation to as many cycles as possible. Because if we can give non-zero circulation to cycles, we can prevent these nice cycles from happening, which have to have zero circulation. And so we're going to prevent matchings from being different from each other. Okay. The problem is we can't do this for all cycles at once. So what we're going to do is we're going to work in stages, and starting with short cycles. We're going to find a weight function from W sub t that gives non-zero circulation to all cycles that are short. And then once we do that, we get a derived graph, and in stages we'll keep working on short cycles in the derived graph and so forth until we whittle ourselves down to a perfect matching. But it turns out, the nice thing, it turns out there aren't that many short cycles, so we can actually do this. But we need a lemma, and so I'm quoting a lemma from I'm sorry, the name's escaping me now. CRS 95. So the lemma says as follows: let S be a positive integer, and let T be S times n squared. N is the number of nodes of the graph. Then for any set of S many cycles, there exists a weight function from our master set W sub t that gives non-zero circulation to all of these cycles simultaneously. And here, T is only n squared times S. So if S is reasonably small, n squared times S is also reasonably small, and so our set of weight functions are going to be fairly small as well. The weights are going to be manageable, and we're able to give non-zero circulation to any number of s many cycles as we want by picking the right weight function from W sub t. We're actually going to apply this lemma with s is equal to n to the fourth. So t here is going to be n to the sixth. And so each weight function from W sub t only needs 6 times log n many bits to describe each weight, because we're taking it modulo some j which does not exceed n to the sixth. All right, this lemma is actually fairly easy to prove, and I'm going to sketch a proof of it right now. So, sorry, I lied. I'm going to talk about the derived graph first. I'll get back to the lemma. We'll prove it eventually, but I'll get back to it. But first, we need a new concept, the derived graph. So, again, we start with G. G is a bipartite graph. And we'll assume it does have a perfect matching. If it doesn't have a perfect matching, our algorithm will find this out eventually. But suppose G does have a perfect matching. And W is any weight function on G. Then we define the derived graph of G with respect to the weight function W. This is the subgraph that you get by taking all the vertices of G's. So it's a spanning subgraph. And E prime, where E prime is just the union of all the minimum weight perfect matchings of G. So you take all the perfect matchings of G that have minimum weight, you take all their edges and you take the union of these edges. So E prime, an edge is an E prime if it participates in some minimum weight perfect matching of G. So this we call the derived graph. And here's the key lemma that we have to prove about the derived graph, is that it turns out all cycles in the derived graph have 0 circulation with respect to the weight function. So, we have a corollary to this, is that all perfect matchings in the derived graph are minimum weight perfect matchings of the original graph. In other words, if you take the union of these edges, you're not introducing any new matchings that were not minimum weight. So all the perfect matchings in the derived graph are minimum weight perfect matchings in the original graph. Okay, with respect to the weight function W. And again, the reason for that is that if you had another perfect matching that was not minimum weight, it would differ from one of the minimum weight perfect matchings with some cycles, and at least one of these cycles would have to have non-zero circulation. Otherwise, you couldn't have a discrepancy in the weights. But the Keylemma says that there are no such cycles. So this is the key lemma that we have to prove. And from that, we get the corollary. We're going to use both of these. It turns out the key lemma, this was not at all obvious at first. And in fact, this was the last lemma we proved. We had everything else in place except for this lemma. And and it wasn't at all clear that this was true. And in fact, well, we know it's true for all nice cycles. We just showed that. But that's not good enough. We actually need to have that all the cycles in the derived graph have 0 circulation. And that was not at all clear. And in fact, there are non-bipartite graphs for which the lemma does not hold. And here's an example of one right here. So if you look at this graph for a second, it has 3 minimum weight matchings. Basically, what you do is you take one of the edges with weight 1, and then you take an edge of weight 0 on the left that doesn't touch it, and an edge with weight 0 on the right that doesn't touch it. This is sort of a threefold prism, so if you can you imagine it rotating in 3-dimensional space, you have a prismatic symmetry here. So those are the minimum weight perfect matchings. And notice when you take the union of all of these matchings, you get back the original graph. But the original graph has a cycle with non-zero circulation. If you just look at the outer edges, the outer rectangle, that has circulation too, not zero. So it's not true for all graphs. And here's a counterexample. And we originally had no reason to think that it was true for bipartite graphs, except for the fact that we couldn't find a counterexample for bipartite graphs. We looked for a bipartite counterexample. We couldn't find one. And we managed to systematically rule out several subcases in the bipartite case. So we eventually did prove this lemma, and we used it using some concepts from geometry, which we'll do. It turns out later there was an alternate combinatorial proof, and this was found by Rao, Spilka, and Vigderson. It was not published by itself, but it was reported and mentioned, and actually with the proof, it was mentioned in a tech report by Goldwasser and Grossman back in December of last year. But I'm gonna give the geometric proof right now. So in order to understand how the Keylemma works, we need to understand the perfect matching polytope. So we're going to take m-dimensional real Euclidean space, so r to the e, where the standard basis vectors are indexed by the edges of the graph. This is like the edge space of the graph, but it's a vector space over the reals. It's not over the two-element field. All right, in that case, any set of edges naturally corresponds to its characteristic vector. So for each edge in E, S sub E, the eth coordinate of S is either 1 or 0. It's 1 if the edge is in the set, and it's 0 otherwise. So it's just a 0, 1 vector for each edge. And now we can define the perfect matching polytope. This is just the convex hull of all the perfect matchings of G. So you take a perfect matching, it's a set of edges, corresponds to a 0, 1 vector. Take all the perfect matchings, that gives you vectors in m-dimensional space, and we take their convex hull, and that's called the perfect matching polytope. Okay, so if G is bipartite, then it turns out there's a way to describe a perfect matching polytope using basically linear constraints, and this we're not sure who proved this first, but it's in Lovaas and Plummer, the textbook in matching theory back from the 80s. If G is bipartite, then you can characterize the vectors that are in the perfect matching polytope by these linear constraints. So X is in the polytope if every coordinate of X is at least 0. And if you look at any vertex and you sum over all the edges that are incident to that vertex, that's delta of V in the summing index here. If you sum over all of those, the coordinates of those equal 1. So this actually characterizes the perfect matching polytope. So if you have a perfect matching, this is clearly true, because you know, the entries are 0 or 1, and every vertex is incident to exactly one edge, and so the sum of these will equal 1. We'll have one term that's 1, and the rest of them are 0. Okay. So it turns out that this is an if and only if. So we can characterize the perfect matching polytope this way. All right. So again, the forward direction of this is clear for any graph. It's not it doesn't have to be bipartite. But the converse actually does not hold for general graphs, but it does hold for bipartite graphs. That's important. That's what we're going to use. All right, so we're going to just take this lemma as given, and you can extend a weight function. If you have a weight function on the edges, you can extend it to this space, m-dimensional space, just by linearity. So if you have any vector corresponding to edges and you apply the weight of that vector, you just multiply each component by its weight and add it up. It's like the expected weight of the vector. Okay. So to prove the Keylemma, so recall what the Keylemma says. The Keylemma says is that if you take the union of all the minimum weight perfect matchings, any cycle in that union has zero circulation. So here's how we're going to set this up. So look at all the perfect matchings of the graph that have minimum weight. Let's call this minimum weight Q. So suppose there are T of them, so x1 through xt. What we do is we can just take the average of all of these. So we add up all of these vectors and divide by T, and we'll call that vector x. Well, x1 through xt are all perfect matchings, and this is clearly a convex combination of those. And so x is in the perfect matching polytope. And in fact, it has the same weight. It has the same minimum weight Q as all of the x1 through xt's, because we're just averaging. We just take the unweighted average of those. All right, it's also clear that every entry in the derived graph, G prime, satisfies x sub e is at least 1 over t. So if you look at an entry of x that corresponds an edge that really does participate in a perfect matching, well then that entry, at least one of these vectors will have a 1 sitting in that entry, and so at least you're going to get a value that's at least 1 over t for that entry. The other edges are going to have weight 0, but any edge that's actually in the derived graph has the corresponding value of x at that edge is going to be at least 1 over t. All right. Now, suppose I have some cycle in C. I have some cycle C in the derived graph G prime, and suppose it has non-zero circulation. So, without loss of generality, suppose that the blue edges outweigh the red edges. Then here's what we're going to do. We're going to tweak the vector a little bit. So we start with the vector x, and we produce a new vector y, and we do that by subtracting 1 over t from all the blue edges and adding 1 over t to the red edges. So we're tweaking x a little bit, and we get a new vector y by doing this. And we're doing this just on the cycle, so we're not changing any other contributions from any other edges. So first thing to notice, very importantly, is that this new vector y is still in the polytope. It's still in the perfect matching polytope. We have not made any edge weights negative, because all the edge weights in the derived graph, all the edges in the derived graph has values at least 1 over t. So we've not made any edges negative, any edge entries negative. And we've preserved the sum of the edge contributions at every vertex. So we've subtracted 1 over t from one incident edge, and we've added it to another incident edge, and so the sum is the same. And so the linear constraints from before are all still satisfied. So y is still in the perfect matching polytope. But what we're doing now is we are giving more weight, or we're favoring the edges, the red edges, which have a smaller overall weight than the blue edges. So if we take the weight of y, what we're going to get is we're going to get the weight of x, but with some correction term. And this correction term is exactly the circulation of C divided by T, and we subtract that. So if the circulation of C is non-zero, then the weight of Y is strictly less than Q, which is the weight of X. But if that's the case, then since Y is in the polytope, Y has to be a convex combination of perfect matchings of G. So one of those contributions must be a perfect matching of G with weight less than Q. And this is a contradiction because we're only taking the we're assuming Q is the minimum weight of any perfect matching. So this is a contradiction on our assumption that we have a cycle with non-zero circulation. So that concludes the proof of the Keylemma. And so the derived graph, all its cycles have zero circulation. Okay. So now let's get back to our goal of removing short cycles from the derived graph. So in steps, we're going to remove cycles from the derived graphs. And each step, we're going to take the next power of 2 and remove all the cycles of length up to that next power of 2. And the next lemma says that there are not too many of these. So here's the lemma. So let G be a graph with no cycles. Suppose G is a graph with no cycles of length up to R. So all its cycles have length bigger than R, and R is just some even number. Then G can't have that many cycles of length up to 2R. In fact, it can have at most n over 4 cycles of length up to 2R. So the idea is, using this lemma, which I'll prove in a minute, we can give all these cycles non-zero circulation by some weight function in W sub t, where t is n to the 6th. And so by forcing these cycles to have non-zero circulation, that means they can't be in the derived graph with respect to the weight function W. So if we pick a weight function W that forces all these cycles to have non-zero circulation, then the derived graph is not going to have these cycles in it by our Keylemma. So so we do this in stages and systematically remove cycles from the derived graphs. So now let me just quickly prove this lemma. So this lemma just says that you can't have that many cycles of length up to 2R if you don't have any cycles of length up to R. So we now prove this lemma. So here's a quick proof. So suppose I have a cycle C of length no bigger than 2R. Well, you can always choose 4 vertices in cyclic order on this cycle, say U0 through U3, in cyclic order, such that the distance between adjacent vertices is no bigger than R over 2. Remember, R is even here. So the distance between adjacent points here is at most R over 2. Well, the key point is that this is the only such cycle given that satisfies this property and goes through U0 through U3 in that order. If there were another such cycle, C prime, let's say the red cycle, so the red cycle is C prime, well, C prime might actually coincide with C on some of it. So for the segment, say, between U3 and U0, and maybe it's the same, but at some point it deviates. And pick some deviation, C prime forms a cycle now with C of length at most R. So the red segments have length at most R over 2. So if you pick some segment where they deviate, they induce some cycle, and this cycle has length no bigger than R. But we assume that there were no such cycles in the graph, so this is a contradiction. Okay, what that means is the number of cycles of length up to 2R is no bigger than the number of ways of choosing U0 through U3. So four vertices from the graph in some order. There are n choices for each vertex. So that gives no more than n to the fourth many choices. And each one determines at most one cycle of length up to 2r. So there can't be any more cycles of length up to 2r than n to the fourth. All right. So here's the outline of the general approach. We start with G0, which is the original graph G. So it's a bipartite graph, and we're assuming it has a perfect matching. We'll call this, so this will be G0, and now we're going to get a sequence of derived graphs. So what we first do is we choose a weight W1 from our set, such that all cycles in G0 of length at most 4 have non-zero circulation. So we know we can do this. And we know that such a weight function exists by the lemma, previous lemma. So we force non-zero circulation for those. And then, given the weight function W1, we'll let G1 be the derived graph using the weight function W1 from the original graph G. So G1 has a perfect matching because we're taking the union of perfect matchings of G. So G1 still has a perfect matching. And in addition, it has no cycles of length less than or equal to 4 because we've given all of those cycles non-zero circulation. And our Keylemma says that all the cycles in G1 have zero circulation. Okay. So now we do this again. So now we're going to pick a new weight function, W2, such that all the cycles in the previous graph, G1, of length at most 8, have non-zero circulation. So we let the next graph, G2, just be the derived graph with respect to W2. Well, this derived graph, G2, still has a perfect matching because it's derived from the previous graph, which still has a perfect matching. But it has no cycles of length up to 8 because all its cycles have zero circulation, and W2 says, nope, there are no cycles. There are no. All of those cycles have non-zero circulation from G1, so G2 can't have any of those. So it has no cycles of length up to 8. Well, so we keep doing this, and in general, on the ith step, we choose a weight function W sub I, such that all cycles in the previous graph of length up to 2 to the I plus 1 have non-zero circulation. And then we let G sub I be the derived graph of that. G sub I still has a perfect matching, but no cycles of length up to 2 to the I plus 1. Okay, so we keep doing this, and we do this basically log n times. And what we wind up with is a final graph, GK. Well, GK, notice that GK has no cycles of length up to 2 to the k plus 1, but 2 to the k plus 1 is at least the number of edges in the graph. So in fact, GK has no cycles at all. But it still has a perfect matching, and so what that means is that GK really just is a perfect matching. So an acyclic graph that has a perfect matching, that will be a perfect matching. Okay, so GK is a perfect matching. And now what we want to show, we've picked these weight functions, and by the way, we don't really know what these weight functions are. We just know that they exist. That's something to keep in mind. The next thing is we don't really have a quick way of finding them. We just know that they exist. All right. Next step is we're now going to build an isolating weight function for G. So the way we're going to do this is we have to glue these weight functions that we've chosen together into a single weight function. So let B be a strict bound on any edge weight from all of these weight functions, W1 through WK. In fact, we can take B to be n to the 6th. So for every edge, we define now a master weight function, W sub E, which is just the sum of the weights of W1, W2 times decreasing powers of B. So notice what this is. You can think of this, if you like, as sort of a base B representation of a weight, where the individual digits are the individual weights. And the most significant weight is W1. That has the highest priority. And then W2 has lower priority and so forth, and W sub K has the least priority. This will be our master weight function, and we claim that if G has a perfect matching, then this weight function is isolating for G. Okay, and if that's the case, then we know that we have an isolating weight function. We still don't know how to get it. But we know that this weight function in particular is going to be isolating for G. So let's actually just show that this is the case. So notice that on each step we're getting a smaller graph. So we're just we're taking a subgraph, a spanning subgraph of the previous graph at each step. So the edge sets of the GI form a descending chain, and they end up with a perfect matching of G. Let's call it M. So M is just the edge set of the last graph, G sub K. All right. Let's suppose I have, so M is a perfect matching in the original graph G. Suppose I have some other perfect matching, call it M prime, in the original graph G. I'm going to show that the weight of M prime is bigger than the weight of M. That means that M is actually isolating, according to our weight function W. So if M prime is different from M, then notice M prime and M are both in G. But only M survives to G sub K. So somewhere along the line, M prime disappears from the derived graph. So there has to be some stage less than K where M and M prime are both still in the graph G sub I, but M prime doesn't make it to the next derived graph G sub I plus 1. All right. So since M and M prime are both all in the graphs G1 through G sub I, they both have the same minimum weight with respect to the corresponding weights W1 through WI because they're all in the derived graphs. So M and M prime are both minimum weight matchings in M1 with respect to W1, and G1 corresponding to W1, G2 corresponding to W2, and so forth. But now, M prime is not in GI plus 1, but M is. The only way that happened was because if you look at the I plus first weight function on M prime, it had to be bigger than the I plus first weight function on M. That's how M prime did not make it into the derived graph. But this means that so all the higher priority, or if you like, the more significant weight functions for the two matchings are equal, but then there's a discrepancy on the I plus first weight function. Well, that just is another way of saying that the master weight function on M prime has to be bigger than the master weight function on M. And this is for any M prime, and so we know that W is isolating. Okay, so how does our algorithm work? Well, we know that these W1 through WK exist, but we don't know which one of them work, so we just try them all in parallel. So for any set of weights W1 through W sub K in our master set, W1 n to the 6th, in parallel what we do is we compute the master weight function W as above, and we know that one of these choices of W must be isolating. Still in parallel, we compute the determinant of the matrix corresponding to this W, as was done in the randomized NC algorithm from before. if we ever find a non-zero determinant, the answer is yes. And if G does not have a perfect matching, then none of these determinants will be non-zero, and so it's safe to answer no at this point. All right. So now the key point is that each component, W sub I, each weight from W sub I takes 6 log n bits to store. So W itself takes log squared n many bits to store for each edge. So processing them all in parallel can be done with circuits of size 2 to the log squared n, and depth log squared n, again using Berkowitz's algorithm. So that's the basic outline. There's some details here. Obviously, I'm leaving out. Let me just keep on going here. I think since I'm running short on time, let me just mention the RNC algorithm. So the RNC algorithm basically says just choose these modular weight functions for random j, for random prime j. And any set of S cycles has non-zero circulation with high probability. And so if we do this k times, we get random W1 through WK, and those work with high probability based on previous considerations. So the RNC algorithm is just an easy extension of what we just did. We have some other results. Most of these results are just based on the fact that many of these problems reduced to are equivalent to perfect matching. So bipartite weighted perfect matching, maximum bipartite matching, cycle cover, subtree isomorphism, max flow with polynomially bounded integer capacities, constructing a depth first search tree. All of these are in Quasi-NC now. All right, thank you very much. I'd like to thank, again, Oded Regev, Clement Kanon, and the rest of the organizers for inviting me to the talk. And the authors would like to thank Manindra Agrawal and Nitin Saxena for their encouragement and very helpful discussions, and also Arpita Korwar, who helped with discussions and the techniques in our RNC algorithm. So that concludes my talk. Thank you very much for listening, and I appreciate any questions that you might have.
Thank you, Steve. So, questions?
So I have a question.
Yes.
You talked about de-randomized algorithm.
Mm-hmm.
It's not clear to me where you actually de-randomize it, because I see that at the end you try to use some RNC algorithm to compute the metrics. Then is that randomized?
Okay. No. So good question. So I think here's the spot in my slides where you saw this. So computing the determinant is not randomized. That is done deterministically. This was a component of the RNC algorithm. The only randomness in the algorithm of Mulmuli, Vazirani, and Vazirani was choosing these random edge weights. But computing the determinants is not random. It's a deterministic algorithm. So there's no randomness there. And we're trying all these weights in parallel. And the point is there are only quasi-polynomially many of them. So we can do that in parallel using a quasi-polynomial size circuit. But there's no randomness anywhere here.
Thank you.
Okay.
Can you go back to the first place where you mentioned this increasing sequence, like this geometrically increasing sequence of weights you used to, like when you first gave an isolating sequence of weights, which I couldn't use. So.
All right, let's see. Right here? Was this the place right here?
No, at the very beginning, like
Oh,
around
okay.
when you first mentioned a very simple choice of weight, but the weights were too large.
Oh, okay. All right. Um, okay, so this was even back before the Keylemma, so I'll just
Yeah, yeah,
okay.
like right after that, yes.
Right. So
When you have the 2 to the W.
right. Let's see. Isolation lemma. Okay. Yeah. Here we go.
So yeah, my question is, so even if the weights are this large, uh, each weight can, I mean, okay, so I do not know what exactly, so determinant can be computed in NC2, but
Hmm.
what, do the weights need to be, is it strongly, is it NC2 in the length of the inputs, or is it like NC2 in the actual integers?
It's NC in the length of the inputs.
So here M is something polynomial in M is like polynomial in N, right? N square, whatever,
Right.
something, right? So each
Yeah.
of the weights is still representable using only poly in bits.
Ah, yes. Okay. Yeah. Good question. Well, actually, no. The weights can be done with polynomial bits, but if you look at the determinant, I got to go back to the determinant.
Uh-huh.
So each entry is 2 to the weight.
Right.
So this is going to be 2 to the I. It's doubly exponential in I.
Okay, right. Oh, I'm sorry. Yeah,
Yeah.
okay.
So yeah, that's a good point. But yeah, it's because we need the powers of 2 to the weights. So these are actually really big matrix entries.
Okay, yeah, sorry.
Okay. No problem.
Do we have any other questions? Um, well, in that case, let's thank the speaker again. Uh,
Thank you.
okay, so we'll take it offline now, but you're welcome to be here. We'll just take it offline.
I can be here. Okay. Yeah. Thank you.